Hi, this is Professor Kleitz. In section 16-3, I want to talk about dynamic RAMs. Although dynamic RAMs, or otherwise called DRAMs, require more support circuitry and are more difficult to use than static RAMs, they are way less expensive per bit and have a much higher density, minimizing circuit board area. Most applications requiring large amounts of read-write memory will use DRAMs instead of static RAMs. The main memory in PCs, in fact, they will be using anywhere from 2, 4, 8, or even more gigabytes of DRAM. So the main difference that dynamic RAMs have over the static RAMs is that their main memory is this charge placed on a storage capacitor. And what I'm showing in this diagram is if after the address decoding is taken care of, let's say we're trying to put a 1 into storage location, in other words put it on a storage capacitor, you would place a 1 at the DN line, which was decoded to this point, and then provide a write pulse. Since this is an N MOSFET, this becomes a short, and the 1, which is plus 5 volts, will be placed on the storage capacitor. And then when you go to read, you would place a read pulse on the gate of a MOSFET, and this creates a short from drain to source, and that allows the 5 volts to be felt at the output. So basically it's the storage capacitor is either going to have a charge or not. Of course, the problem with using a capacitor is that the charge doesn't last forever, so we will have to refresh every 20 or 30 milliseconds. We'll have to read the capacitor. If there's a 1, we have to recharge it and recharge it over and over again, and it tends to decrease over time. So again, we have to keep refreshing these capacitors. In figure 1611A, we can look at the logic symbol for the 2118 DRAM chip. This is configured as a 16K by 1 memory chip, so 16K addresses. Now 16K is made up by the fact that we have 0 through 6, and this is actually going to come in as a row address, and by pulsing the RAS row address strobe, and then we're going to change this to columns, and we're going to pulse the CAS, the column address strobe. So actually what we have is A0 through 6 duplicated for a total of 14 address lines. And as we know, 2 to the 14th power is the same as 2 to the 10th times 2 to the 6th, which is 16K. So with a 7-bit worth of row addresses, that'll give us 128 rows by 128 columns. You multiply those two numbers together and you get 16K. At each location is only a single bit. And as we can see in this diagram, we have a single D out and we have a single D in. We also have a write enable, which when it's low we're writing, when it's high we're reading. And again, we got the not RAS and the not CAS. So let's look at the timing involved in this. Oh, and by the way, up in logic symbol, here it is, A0 through 6, the not RAS, not CAS, not WE, and then the D in, D out, which are actually separate terminals. Now the reason they have a separate row and column address strobes is so that we can keep the pin count to a minimum. With 2 to the 14th power, we would actually have 14 address lines. So they've cut the number of pins by 7 by cutting it in half and just having 0 through 6, which would be 7 lines with the RAS, and then 0 through 6 for the column. So we've saved on pin count that way. So there is some precise degree of timing that takes place. So on the address bus, what we'll do is set up the address, the row addresses on the A0 through A6, and then we'll drop the RAS line low. This high to low signals the DRAM chip that it has valid rows. That goes into a row decoder, and then we take the address bus and we change it to the columns. At this point, now we have valid column information. We drop the CAS line low. Now the column addresses go into the column decoder. So now we got the row columns figured out, and there'll be a length of time after the CAS called the TCAC before the valid data is output at the address or at the data bus. The other time that we have to be concerned with is the T rack, which is the length of time it takes from the row address dropping low, the RAS signal dropping low, to when we have valid data out. So you have to look at the worst case between the T rack and the T CAC to find out when you'll have valid data out. So similar timing takes place when you want data in. So data in means that we're writing to this device. So you drop the RAS, you set up the row address ahead of time, and then you drop the RAS low, and then you set up the column address and you drop the CAS low. But there's a certain length of time, TDS, which is a setup time, where you have to have the data valid at the input before you drop the CAS low. And then there's a time called the TDH, which is the whole time afterwards, where you got to hold the data valid after the CAS drops low. So it seems like a lot of work demultiplexing the addresses. And by the way, we did have to demultiplex them because the address bus is going to be A0 through A13. We've got to split those 14 lines into 4 lines and 4 lines. So there is a demultiplexing on the front end. And then we also have to refresh the memory cells and deal with the RAS and CAS. Well, most manufacturers of DRAMs had developed a controller ICs to simplify this task. Some of the newer dynamic RAMs have refresh and error detection correction circuitry built right in, which makes the DRAM look static to the user. It looks just like an SRAM. So one popular dynamic RAM controller is the 3242, and what we have here is the row enable line. When this is high, the address bus, which is going to be 14 bits wide, A0 through A13, the first 7 lines will be split off and sent out to the NOT Q0 through NOT Q6, which are 7 lines provided to the various DRAM chips. We're going to line up 8 DRAM chips, one for the D0, one for the D1, D2, all the way up through D7 going out to the data bus. So again, the row enable takes the first 7 of these address lines and sends them out, and then when the row enable goes low, we're talking about columns then, it takes the last 7 bits, which would be A8 through A13, and send those out. And this is also coordinated with the RAS and CAS signals, so the DRAM knows when it's looking at the low order rows versus the high order columns. This dynamic RAM also has a refresh enable, and when this is made high, the counter counts through all 128 columns in an entire chip, and it refreshes all the capacitors. Basically, it looks at each capacitor in the columns, and it determines if any of them are high, it recharges them. And so this runs at a speed dictated by the count frequency on the count line. So to get these precise timing waveforms, they do have delay chips, so you could come in with a single pulse and have multiple taps on the output. And this is set up as a 50 nanosecond delay line. So when the input signal comes in, 50 nanoseconds later on T2, you'll get the exact same duplicate signal, but it's going to be skewed over by 50 nanoseconds. So when we went from this low edge to this low edge, the fact that there was 2 different taps, so this one was 50 nano inverted, this one is going to end up being 100, so we have a 100 nanosecond delay from this low edge to the first low edge. We'll use that for our row enable, RAS, and then the CAS will go another 2 taps to get off another 100 nanosecond delay from that. So these give us precise timing delays that we need for our RAS and CAS signals. And in table 16.2, I've got a sample of some Hitachi low-power DRAMs. These are actually pretty small by today's standards, but you can look these up on the internet and see the higher megabit. And by the way, the lowercase b means bit. If it's an M capital B, that would be byte. So these are set up as this particular one. It's 256 megabits configured as 32 mega locations with 8 bits at each location. So the configuration is given in this chart also. These are kind of a low or medium voltage. They're not the 0.5. They're actually set up as a 3.5 volt memory cell. And they also have the 2 volt and then the 1.2 volt memories also. So a margin annotation that you'll see talking about inside your PC says here that modern PCs use 2 gig, 4 gig, or even more of DRAM. To physically mount so much memory, manufacturers solder several memory ICs onto a single board, which is then inserted into a special socket on the motherboard. These memory boards are called SIMs, single inline memory modules. There's also DIMMs, dual inline memory modules, or RIMs, which are the RAM bus inline memory modules. As memory requirements increase, these memory modules can be easily upgraded by the user without any special tools. And you can look all this up at some of the websites listed for you in Appendix A. So another type of memory is called the ROM chip, and we'll look at that in the next section.